quizzes leading to this exam that you're gonna have next week on Tuesday, okay? So I'm also gonna go over again the standing waves, and let's start. So there's no waste any more time. I'm recording this, so should be okay. Let's take a look at the quizzes. So you had quiz 4 and quiz 3 before this exam, right? Let's go back to quiz 4, just to re-review a few things in there. So, for the scientific definition of temperature, you have to remember that is the average kinetic energy of particles, okay? So that is important. Some people wrote that it was the measurement of cold, or how heat, or how hot, or how cold a substance is. That's not the answer. Okay, temperature, the scientific definition, is the average kinetic energy of particles. And you should remember that if you have, for example, if I ask about the states of matter, it would be a good idea to draw this figure of particles in fixed positions, right? Sort of. We know that they move, they vibrate a little bit, because to stop the molecular motion of any object in nature, you will have to go to the absolute zero. So any object that you see at room temperature, even though it looks solid in shape, the particles are vibrating per se. So sometimes we model them like having a string here, right? It's just a model, doesn't mean that there's a string. It's just to characterize the vibrations, oscillations per se. So that, and that. So a solid, right, has a shape, a fixed shape. For a liquid, you have particles already randomly moving, not totally divided though, okay? For a gas, however, you do have more random motion. And you can have collision between the particles. So the kinetic energy, if you think about it, goes like this. The best example would be like saying ice, liquid, water, and steam. You have to add more kinetic energy, or more temperature, more energy, which is illustrated in the increase of temperature, to observe the change of state, right? Okay, examples for heat radiated via conduction are basically if you touch any hot surface, then you will have, right? Another example will be if you have a conductor, a metal conductor. It could be copper, it could be iron, it could be silver, and then it can be a long bar, right? And then you approach it to say fire or an oven, right? And you see, the best example will be that when you have a kitchen tool, right? It needs to have some sort of a handle of wood or plastic, normally wood, because wood is a bad conductor of heat and electricity. So then it doesn't get hot. The metal part gets hot, but the handle does not. So whenever you buy, now you know, right? Whenever you buy a kitchen tool, right? A scoop or whatever, it needs to have a handle normally made of wood, so it can actually protect your hand, right? So that's heat via conduction. Radiation is a microwave. It could be a heating device, and also the sun. The sun radiates energy, and we get it in terms of heat, right, here on Earth. Okay, so when they tell you that a gas is being compressed, that means that the energy, the work is done on the system, on the gas. So that work is negative. Another way to visualize this is by, and we didn't really talk much about it, but work is proportional to pressure and volume in the first law of thermodynamics. So for thermodynamics, so we're right now reviewing chapter 5, by the way, thermodynamics. When you exert, well, work is proportional to pressure and change on volume. So if the change on volume is negative, like compression, then the work is indeed negative. And obviously, you are applying that force, so that's a work on the system. So there was a problem in there that said that you are applying a force, compressing a gas, and you release energy in 850 joules. So the work done on the gas is 850 joules. The change of internal energy is 1250. Find the heat released or absorbed by the system, by the gas. So remember, Q equals to work. I corrected this equation, right? I might upload a secondary source, another set of slides. The slides that we use normally in class are based on your book, but I do have slides from other textbooks, so I might update that chapter. I believe that's chapter 5, right? Where we talk about heat, conductivity, linear expansion, and thermodynamics. It's just a little section. So this is the equation. So obviously heat will be equals to minus 850 because it was a work done on the gas plus 1250, the change of internal energy. This gives you 400 joules. So it was heat absorbed by the gas. And it makes sense because you're compressing it. So it's heat absorbed. By the gas. Everybody got this right? The heating curve, whenever you see horizontal lines in a heating curve, you are looking at a change of state. I told you it was a block of ice. So those two represent ice, solid to liquid, liquid to gas. Right? That is latent heat. And as you probably, and as I know, you know, because I saw in the quiz, latent heat is heating energy given to a substance to change phase. We call it latent because this heat depends only on the mass and a value of latent heat of fusion or vaporization, right? Or latent heat for melting or boiling. It doesn't depend on a change on temperature. So a substance changes state when increasing its potential energy. That could be a question in the exam, by the way. Okay? You increase the kinetic energy, you increase the temperature. But in those horizontal lines, right? In the heating curve or cooling curve, by the way, right? If you are cooling an object, it's the same energy, but a different process. It can be condensation, solidification, right? But if you have this, and then this, right? Here, the temperature is constant. This is the temperature, by the way, in Celsius. And here is the energy, heat in joules. this could be this 0 degrees, right? So here is let's say minus 20. So here, way up is 100. So delta T is 0. No change of temperature. However, we know there is a QL, right? QL is equal to ML. It can be LV, in this case would be LF. And I gave you, and there was a problem like that. Compute the energy needed to heat 2 kilograms of copper from 20 to 70 degrees Celsius. That was very easy, right? You just have to do the equation MC delta T. So I'm going to do another one today, but pretty much if they ask you to compute the heat for a mass of 2 kilograms of copper, where the C of Cu, copper, is 385, I will ask for sure, so I didn't ask on the quiz, I will ask what does specific heat mean? And you should know, based on these units, joule per kilogram Celsius. You should know that that means, or specific heat means the energy required for 1 kilogram of any substance to increase by 1 degree Celsius. Alright? So water has a very high specific heat. That means that we require a lot of energy to heat water. Hence, why it takes so much for water to increase the temperature and to boil it. Also, that means even though the composition of seawater is different, but we know now, kind of, right? We explained on chapter 4 the physics of hurricanes due to the high temperature of the water, of the ocean water, and producing those high currents due to the difference of temperature with the environment and the humidity, right? I mean, it creates those very high speed winds and then the hurricane. But when we discuss about climate change, because it's not really global warming, by the way, it's climate change, because what we see, we're seeing that the weather system seems to be shifting more rapidly than what it should. So MC delta T, right? MC delta T 50. 2 times 50, 100 times that. And I think a lot of you got this answer. Joules. What we see with the weather system is that there's a change on the temperature, like the melting of the polar caps, right? And we start thinking in terms of physics, how much energy we need to just increase all the mass of the ocean water by just 0.5 degrees Celsius. You may think it's not much, but it's a lot, because the specific heat is 4,186. If you multiply by 0.5, that's 2,093. That's okay, but the mass is billions of tons of water. So that's a lot, right? And then with thermal machine, the thermal machines will also be asked. This time I might ask about a Carnot. So let's actually use this problem where I gave you the heat in the hot and the cold source. So with thermal machines, which is a direct, they call it a second law of thermodynamics, but it's actually a direct application of the first law, the conservation of energy, right? The first law of thermodynamics is a conservation of energy. No system has 100%, well, I mean, conservation of energy. Let's start with this. The expansion, So thermal machines do expand the idea a little bit more, because they say that the heat on the hot source is never the same as the heat given as the work, done by the machine, right? It's like, for example, all the energy that you have, you cannot use it to do work by exercise or whatever. There is always some sort of lost energy. That will be your QC. Now, each of these are related with some temperature. You have the temperature in the hot spot, and you have the temperature in the cold spot. If the machine is not Carnot, so it doesn't follow the Carnot cycle, then yes, we can say that the machine just have the following efficiency. So then the efficiency is work divided by Q in the hot spot, which is equal to 1 minus QC over QH. Why is that? Because QH is equal to work plus QC. Only if it's Carnot. If you have a Carnot cycle where we maximize the efficiency, we maximize the efficiency by doing 1 minus the cold over the hot. There will be a question like that in the exam, okay? 900 joules hot, 200 joules cold. So let's put the data here. If they tell you that QH is 900 joules and QC is 200 joules, then the work done will be 700 joules. This minus that. Right? Yeah. And the efficiency, work over QH multiplied by 100% done. Okay? So 700 over 9, that's how much? That's around 80 something percent. It's around 78% approximately. Okay. So the quiz actually covered, the only thing that we didn't cover in the quiz was linear expansion, right? So that might be asking the exam. Remember the equation was that on a hot day of summer, for example, right? The heat given to any object will be translated into a change on length, right? So it will, the heat transfer to an object, you will see it as a change, as a dilation. And this is applied in railroads or even in the pavement. When you see the pavement that there are some gaps, it's because they know that that material in particular during summer will expand. Okay? So let's see if there's another problem here. I think it would be a good idea to check at least the weekly problems for this. This is waves, this should be heat. Oh, did I put it here yet? Oh yeah, this is the one. Yeah, week 7 is oscillations. Oh, this is a good one. When I ask you to melt ice, but I want to give you ice. A block of ice. I want to give you 200 grams of ice at minus 10 degrees Celsius. And the idea is how much heat do you need to melt all the ice? The way I like to explain this type of problems is by doing a line where you locate at the beginning the minus 10 degrees Celsius, and then farther on the right, the 0 degrees Celsius. And then you're going to say this. To melt the ice, first I need to bring it to 0 degrees Celsius. So I have to heat up. And then on 0 Celsius, to melt it, you don't have to increase the temperature. You just have to give enough energy to melt. So we use this vertical line to illustrate the phase change. This is your phase change. So, what would be the energy? You can say Q to go from minus 10 to 0 degrees Celsius plus QL of fusion. We have the mass of ice. The only thing that you will need is this, that the specific heat of ice is equal to, actually, yes, 2093 joules per kilogram Celsius. It's half than the one on water. So to heat the ice, I need a mass of ice in kilograms, the specific heat of ice, and what's the change of temperature? From minus 10 to 0 is 10 degrees. It's not minus 10. First of all, it doesn't make sense to talk about negative energies. Second of all, because you go from right minus left. 0 minus minus 10, 10 degrees. So we go here and we say 10 degrees. Okay. That you will add $200 grams multiplied by 33.4 times 10 to the 5. That was the latent heat of fusion. Oh, times 10 to the 4, sorry. And then you do the math here, right? I mean, it's just a multiplication. 4,186 I get here, plus, so, 3, 1, 3, 2,000 times 33.4. How much is that? Let's see. So as you can see, right, that's a problem where I'm applying both the MC delta T and the ML, which we have done 66,800. So a lot. You should expect a lot from this number, okay? That's because of the big latent heat. 7,986. So the total heat will be 7,986. So you can see how much lot of energy to just melt 200 grams of ice. It's a lot. Okay? Now, we know that this is ideal. When you heat or cool something, there is always some heat lost in the surroundings. So that is something to think about. Okay? Normally, when we do this in the lab, we use a perfect calorimeter. If you have done a lab on this, which I'm not completely sure if you did, but if you have, then you will know that you use simulations with computerized data. So you don't have much error. There is a lot of error when we do this in the lab. Okay? Because of the tools that we use or just because of the concept itself. Right? To have all this working, you need to have a perfect insulating device. Have you ever wondered why your water bottles or your coffee bottle is made of such a material that, or how is it made so it keeps the heat? That's basically a calorimeter, because the material inside is a perfect insulator. So you can have coffee or cold water in the summer there for quite long periods of time. A cooler works that way, right? So that's something to keep in mind. All right, that has to do not with specific heat, but conductivity. And we talk about conductivity, right? When we saw, for example, said about touching your foot after a shower on the floor, on the tile, or on the rock. You feel colder on the tile because of how it's being conducted, right? The rock is a very poor conductor, so not much of the heat will be absorbed from your foot. But if you touch a tile, it is, and then you feel hot, cold. Okay? All right, so let's review chapter 4, which talks about density. I mean, you know how to compute density. Let's take a look at that quiz actually. Where is it here? Quiz chapter 4 here. What's the definition of pressure? Is the force per unit area. Okay? Is the force exerted per unit area. And the pressure can be felt everywhere, not just if you are on a plane, there is a pressure on the window. There is pressure on the walls of a pool, at the bottom of the pool. Because there is forces acting everywhere. Okay? If I give you a problem where you have to find the pressure given the force and the dimensions of a window or the floor or anything, you have to change the units. That's what some people didn't do in that exam in particular. I gave you a 20 by 30 centimeter window. So some of you multiply this, but don't forget, if you multiply, you get 600 centimeters squared. So you say 100 centimeters in 1 meter, and again 100 centimeters in 1 meter. So that will give you what? 0, 0, 0, 0. So we'll get 0.06 meters squared. So the force in newtons per meter squared, I gave you a force of 200 newtons. The pressure is 200 over 0.06. That will be, this is a calculator for this. Don't forget the units. When you get, 3,333. 0.3 period. You can write newtons per meter squared. That's fine. Or pascals. Those are the SI units of pressure, okay? Pascals. The fourth state of matter, you know, solid, liquid, gas, and plasma. Plasma is just superheated gas conductor. Don't forget, the best way to illustrate it is the star, the sun. The sun is basically in plasma state, the surface of it at least, okay? Actually, yeah, I mean, there is a convection and radiation zone, but I mean, you can say that the sun, stars are basically in that fourth state of matter. And then we have the other exotic ones like neutron stars, black holes, white dwarfs. The problems with buoyancy were not that complicated. I mean, you just have to use a formula. It's asking you to compute the buoyant force acting on a piece of balsa wood with mass, density, and if it's totally submerged, immersed in water, right? So buoyancy is the density of the liquid, which they give you. Gravity, okay, so you need to find the volume of the body, given the mass and the density. So this is a good problem, so we can actually use this, right? So it was 15 kilograms with density of 250. So the density of wood was 250 kilograms per meter cube. And the mass of wood was of 15 kilograms. So you should remember that density is mass over volume. So from here, density is mass over volume. Density is 250. The mass is 15. Volume is what you want. So volume was 15 over 250 meter cube. So to find the buoyancy, you just apply the formula. Density of water times volume times gravity, which is 9.8. Yeah. So the buoyancy would be what? The density, density of liquid, 1000 times gravity times 15 over 250. That's the only thing you had to do in that question. I might ask you this exam to explain the Pascal principle, which is telling you that in an isolated system, enclosed, the pressure at any point is constant, is the same, right? Pascal principle application is in hydraulics, okay, in your system of brakes, right? In fact, if you have kids or you have nephews, like I do, for example, right? A good application for this on a science fair could be using Pascal principle to create a small machine. You can find experiments online, or a press, right? A student of mine a couple of years ago, she did that, and that actually worked pretty good. I mean, you use a couple of needles, and you know when a needle is empty, it has air. If you connect that needle with a tube, you can exert pressure, and then that will go, due to Pascal principle, the system is closed, right? The air inside is a fluid, right? We talk about that as well in chapter 4, right? The air can exert buoyancy also on a balloon. Anyway, so that pressure can be transferred, and then you can create a nice press. You know, the ones that they use to, for example, in garbage disposals, right? To press against and then destroy a cup of aluminum, for example. So you can do that. So if it's connected to a piece of wood, it will make it go down. Now, the piece of wood might be larger in area, right? So how does the Pascal principle works? That needles have a very small area, and because the pressure is the same, force divided by area has to be equal alongside the whole system. If your area is small, very small, then you have to apply very small force to give enough force to a very large area. So that will go down. Okay? Which is what I explained you in class with a piston trying to lift a car, right? Which is a problem that you guys had. Let's actually do it because there were some mistakes in that. How do we use Pascal principle? And then we can go into harmonics, chapter 6. In chapter 6, there's not much to really ask. I will ask about the velocity of the wave, the harmonics in a closed and open tube, and maybe a standing wave. This standing wave problem actually I'm going to do with you guys today. So, to use the Pascal principle, right, I gave you a small piston with area 50 centimeters square. So, the small piston has an area of, again, I told you be careful with the units, right? And you want to lift on the other side a car with 4.5 tons and an area of the piston. So in a large piston you have a car with area 2 meters square, right? It was quite a lot. And this one has a car, but guys, remember the mass of the car was 4.5 tons. And I even told you this, 1 ton is 1,000 kilograms. The first step was for you to find the mass of the car. The mass of the car is 4,500 kilograms. But also the weight. Because based on this, you can put here area 1, area 2. Force 1 over area 1 equals to force 2 over area 2. Force 1 is what you want to know. How much force you have to apply. Area 1 is 50 centimeters square. So, okay, let's put it here. 50 centimeters square times 1 meter square has 10,000 centimeters square. So this will be 5 times 10 to the negative 3. So 0.005. Now I do my problem. F1 over this equals to F2, which is not this, is this multiplied by gravity. I think that's the only thing that got you guys. This is force. So you need the weight. Actually, I might ask a question like that again on the exam. Define Pascal principle and then apply it. Maybe. So there it is. Okay. If you are curious about the answer, a 110 newtons. .25. Think about it. That's not much, right? That's not even the weight of a person. No, yeah, way less than that. That's almost 11 kilograms. Okay, not much. Study buoyancy, study Pascal principle. Bernoulli, yeah, I mean, there was the area times velocity, caudal that we studied. Pressure density will be there, okay? The states of matter, okay? The exam, oh yeah, by the way, guys, so we have to agree again, like we did with exam number 1. Since the exam is on Tuesday, I think we should have the exam like we did. We start at 3 o'clock, 3:10, not 3 o'clock, 3:10, up until 4:45 or 5, okay? So you have enough time. Do not wait until the last minute to submit it, which happens a lot, okay? 10 to 15 minutes before the exam is due, you have to make sure that you are already either scanning or taking pictures, okay? All right, guys, let's take a look at chapter 6.
Hello,
and as I said,
Professor.
with chapter 6, hello?
Professor, it's not good
Hello?
for me at 3. Yes, it's not good for me at 3.
Oh, I cannot listen very well. Can you speak up? Wait, madam. Can you, okay, what was that?
It's not good for me at 3. I can do it at 3. Can I show up at the same time we used to have?
Okay, yeah,
30?
that's fine. Yeah, that's fine. Whenever you can, then I'll give you the time that you need, okay? The extra time,
Okay,
so I can give you the extra 20 or 25 minutes. That's okay. Yeah. Yeah, so I'm gonna, I will open the room, not like today. I will open the room way earlier, all right? And then, in fact, maybe I can open even earlier. So if you have any questions, I'll try to do office hours actually this weekend, all right? Let me think about what I'm doing this weekend. So tomorrow, no. Saturday. Yes, I think I can throw you guys office hours on Saturday, maybe in the afternoon, between 4 and 5 p.m. I will send you the confirmation. The office hours will be via Zoom, okay? So just come in, you have any questions, I'll be at home, all right? Just answering whatever you need. Chapter 6. There's a problem on chapter 6 that I wanted to show you guys, but let's go into the concept. So for chapter 6, you need to know transfer waves, longitudinal waves, what are the differences, examples of transfer waves, light, P waves, of seismic waves, sound, okay? Longitudinal waves, you just have springs, or S waves in seismic waves, all right? The waves in the ocean can also be modeled as transverse waves, okay? Where the velocity of propagation is perpendicular to the direction of vibration or oscillations, right? What is the wavelength? Is the distance between the valleys or the peaks of a wave. A wavelength is how much a wave travels in one period, all right? And the wavelength, we denote it as lambda. So we're doing now chapter 6 sort of revision, all right? So there are a few equations that you need to know, not many, but there are a few things in here. There, yeah? Or, so this is the wavelength. Or, if you keep going, right? This. lambda. Now, lambda is the velocity of the wave times one period. The wave we're assuming is going like this with some velocity, speed. In this case, they both are the same. But we know already, we introduced the idea of frequency, which is the number of cycles per second. So 1 over the period. If we apply this, then the velocity of the wave is equal to the wavelength times the frequency. So that's going to be in the exam for sure. Examples for waves, right? The wave equation to describe any mechanical wave that you can do on a rope, okay? And you can have also superposition of waves, right? When two waves come towards each other, there can be constructive or destructive interference or superposition. If they superimpose constructively, the amplitude gets bigger. If they do it destructively, then it becomes flat. All right? Sort of like when you are in the radio, you're listening to the radio, and then all of a sudden, you are going, and this happens a lot around Edison, by the way. If you drive around that area, you will notice that your radio goes in static a lot. That static is due to the interference of your radio signal with the whole area. You know that area of Edison and Middlesex and Piscataway, they have a lot of antennas. There's a lot of places where they do call centers and stuff. So those signals are going to interfere with your radio. So then you have a lot of static or interference. That's destructive interference, by the way. Right? I also explained you the interference and diffraction of light. That's another phenomenon that we can study with waves. Right? And the other one that I think for sure you need to study is the one of the Doppler effect. All right? So with the Doppler effect, I said what? I said that if you have a source moving away from the observer, the frequency and wavelength will change. All right? Because that you see there will be either stretched or compressed. If the source is moving away from you, the wavelength will be stretched. So you will observe a longer wavelength, but a shorter frequency. If you have a smaller frequency, even though you don't need to do much of this, the smaller the frequency, the less intense, the less energetic you will notice the wave is. If the source is coming towards you, the frequency increases. Like when you have an ambulance coming towards you, and then you hear the siren more loudly. In the case of the ambulance going away, you will see the sound fading as it goes farther and farther from you. That's because of the Doppler effect. There is Doppler effect for sound and for light. The one that we use more commonly here on Earth is the one on sound. The one on light, we only observe it for redshift of galaxies moving away from us. Okay? Should you know the equation? I mean, I'm not going to ask you to compute any change on frequency. All right? But I guess you should know, right? If I give you an example that the wavelength will decrease, why will the wavelength decrease? So, let's suppose the source is moving towards you. If that's happening, the lambda observed is equal to the real lambda of the source, C minus V over C plus V. Sorry, it's not C. It's velocity. Velocity of sound, velocity of sound. Okay. So there it is. frequency will be the other way around. The frequency observed will be the frequency of the source there. All right, let's do the standing wave problem. So a standing wave is produced how? When both ends of the string are fixed, like the string in a guitar, and then you vibrate it, and then you will have a tone. Now we know how those tones are produced. Those tones are produced due to the nodes and antinodes. When you have an open-end tube, two ends open, we talk about the harmonics, 1, 2, 3, 4, 5. When you have a closed-end tube, and open, obviously that's how the sound enters, you have overtones. I was taking a look at the experiment that you guys had in the lab, and actually it wasn't really the case of a resonance tube. It was just a case of notes. And just looking at the chip, look, if you guys have a tube, should I ask you that in the exam? Maybe. So that question that you guys had with the water is a very interesting question for exam, by the way, where you have to compute the speed of sound. I believe you have water here, and was like this. Yeah. Like that. Like that. So what you have to realize, actually, note there, spot. Like that better. So there was a node and a node there. So if I give you a wave situation like that, you should know that this is half a wavelength. Let me see something. Yeah. So this is a wave, right? This part. It's a half a wavelength. You're not seeing this yet. It's gonna be like this and then like that. So that will be a total wavelength. So this is a water. If you realize that and you had the scale in the problem, then you will get the lambda, this distance. What's your lambda? And then the velocity of sound was lambda times the frequency that produced that sound, which was a fork. So it is similar, but not the same, because in the two open tube, we had a different sort of shape, and you already know, right? You can have a quarter of a wave. So this is the secret. For the open-end tubes, two ends open, you have half wavelengths, always adding and adding more. So you first have half a wavelength, then you have a total wavelength, then you have 3/2 of a wavelength, and so on. So you have length and a half, 12, and then you have L. So you have lambda, half, lambda, 3 lambda halves, and then when you rearrange the equation, you have lambda over 2 or 2L, L, 2L over 3, and so on, right? So that 2L divided by N is the wavelength. Yeah, right? So the general rule will be that if the wavelength is 2L over N, then if we're gonna get the frequency, will be N over 2L times the velocity of sound. Well, there it is. But with the tube that is closed in one end, you have a quarter of a wavelength repeating. But each time you add another wavelength, that's the difference though. Sorry, you add a half a wavelength. Each time you add a half wavelength. So it's similar to the first one, right? I mean, you add half. Oh, that's why. There you are. That's the way for you guys to understand. For the two open tube, you have half. You have first half. Then you have half plus half, a total wavelength. Then you have a total wavelength plus another half, free half. And then you have another half. You have twice the wavelength in the fourth harmonic, and so on. For a tube that is closed on one end and open here, you have first a quarter of a wavelength. And then you always add half more. But a half plus a quarter is 3/4. If you add another half, you get 5/4. So you have 1/4, 3/4, 5/4, 7/4. So then it's only 1, 3, 5, 7. Only odds values for N. So the equation becomes the same, but N over 4L. And N is only odd. That's it. That's the only thing you need to know for that. So it's not a very long chapter, but the concept can be a little bit. So if you guys have still some confusions, look at the problems in there, okay? Look at the web assign as well, and then you can ask me questions on Saturday, okay? Let's do this problem. So you have 1, 2, 3, 4, 5, so 6. So you have here a standing wave. You have 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. There. So you have the antenna, the length is 2 meters, fixed at both ends, and they give you the speed. What's the frequency of that standing wave? So it's moving with some speed of 18 meters per second, so it's just a mechanical wave. And the length of this string is of 2 meters. You can also be given this problem and then you have a weight attached here. It will be the same. Because remember, the other equation that you should know is that the velocity of the wave is equal to the square root of what? The force applied, attention, over the linear density, mu. Mu is the mass of the rope over the length of the rope. Okay? So, what's the frequency? You have 1, 2, 3, 4, 5, 6. You have 6 anti-nodes. And 1, 2, 3, 4, 5, 6 as well. Nodes. So 1, 2, 3, 4, 5, 6 anti-nodes. So for a standing wave like this, you always use this equation. The N over 4L is a particular situation where one of the ends is open and the other one is closed. In this case, you have that. So, and it's mechanical, it's not sound. The frequency will be 1, 2, 3, 4, 5, 6 N over 2L times 18. That's it. Very easy, right? So 6 times 18 divided by 4. Wait, 3 half, 27. 27 hertz. So for any standing wave, that's how you get a frequency, where n is the sum of antinodes or nodes. But the nodes, remember, you count them from here. 1, 2, 3, 4, 5, 6, okay? But it's easy, you just count how many bumps. That's basically that's how you get the frequency. That's for a standing wave. Let's see. Oh, this is a good one. You have a string with some mass. So now they give you the mass of the string and the length, and they give you some tension. They give you the vibration of the third harmonic. And this vibration causes a sound wave. What's the wavelength of sound? Okay, so if you have, okay, in a problem where they give you a string and there is a tone attached, you are talking about standing waves. The only type of strings that will give you tones, sounds, in other words, are standing waves. If they don't give you any pipe, like resonance pipes, then you use the equation there, that equation there. All right? And why do you need that? Because they give you the mass of the string, the length, the frequency, and they give you the speed of sound. They want to know the wavelength of it. Do you need a mass for this? MOL, tension. Yeah, they give you the speed of sound. So let's do that. In fact, let's use that problem to practice this as well. The tension is every guitar string, for example, right, or violin, is being attached by some tension there. So when you press it, right, you hear a tone. So if they give you the length, which is 0.67, and they give you the mass equals to 2.0 grams, and they tell you that the harmonic is free in the third harmonic. Let me just see something here. I think you just have to do 2L divided. Yeah, so they give you even more information than what you need. So that's not that interesting because they give you the harmonic free and they give you the length of the string. And if I'm not mistaken, yeah, I mean, they give you the harmonic and they give you the length. For any standing wave, the wavelength will be 2L divided by N. It comes from this. So 2L .67 divided by the harmonic, that's 0.45 meters. All right. All right, guys. I think that will be enough to apply. We apply some of the basic equations. Okay. Study that. Not study guide, but those problems. I uploaded in modules the other set of slides that you should use, and then there are some videos in Canvas where you guys can take a look at waves, sound demonstrations per se. Okay, and that lab that you guys did should help you as well, where you found out speed of sound. All right. So again, if you have any questions, office hours this Saturday in the afternoon. All right. All right, guys. Stop the recording. And